Yeah, okay, welcome back. So let's carry on with our lectures here. Okay, we briefly go through these two types of the random variable, discrete and continuous random variable. So you have actually learned this in your undergraduate courses already. So we just briefly go through it once. Okay. So I think this is clear. X is a discrete random variable provided the image, if that X is a countable set such that P of X equal K is equals to 1. Yeah. So this idea. We only concern with the point whereby X has non-zero probability. Yeah. So provided the set whereby X has non-zero probability is a countable set, so then we call it this is a discrete random variable. Okay, so this is okay. So then we have this as a simple examples. Okay, so if X is a random variable, so then we have a mass function P equals X equals K is like that. So then Fx equals this. So we just submitting all of it. Okay. So this is straightforward. Okay, maybe we shall look at it. So this is the continuous random variable. So which is actually close related to the cases that we discussed in our chapter 1 earlier. Okay. So chapter 1. Oh, okay. So which is close related to this criterion over here. Okay, this is chapter 1, propositions 1.3.1. Okay, we consider omega is R and F is the Borel sigma field. Supposing we have a non-negative function F such that if we integrate this function over R, the whole of real number, this is 1. Yeah, two criterion. First of all, must be positive. Secondly, the integration of F respect to R must be 1. Then we can define our probability to be like that. Okay, so this is one of the criteria for us to check whether a given probability, a function is a probability or not. Okay. In fact, this is the so-called the density function for a given random variable. So let's come back to that. So this is a case over here. Okay, so compare that. Okay, so this is how we define so-called absolutely continuous random variable. So we said that X is a continuous random variable, provided we can have a non-negative function F such that Ft equals to this. Is the distribution function is given like this. So then we can have this. So X is continuous. So provided we have a non-negative functions F, and secondly, so the distribution function is given like that. So in fact, when we have this, right, because of the properties of our distribution function, automatically we can have this. We integrate F from negative infinity to positive infinity, it must be 1. So from 2, so these two, they are identical. So if we go back to this, right, so you can see how we define our properties. So P of this will be, P of any set will be, we integrate over that set here. So that means then we can actually have number 4. So in this case, the probability of we can say x. So that will be we integrate the function f over the Borel subset or the event A here. Okay, next, this is the relationship between the capital F and the small f, the density function and the distribution function. So which is given by that. So if the density function is given, so we can use this formula to compute our distribution function. The other way around, if distribution function is given, so we can use this formula to compute our density function. So we can put it here. So ft is equals to f prime. So I think now these examples are so straightforward here. Okay, supposing x is a random variable, the f is given like this, the distribution function given. So we can use it to calculate our the density functions over here. So we look at this. Okay, so our function f is given like that. Okay, maybe I put it here. So f of x is equals to 0 when x is less than 0, and x when this is 0 to 1. So if you look at the graph for the functions, so it could be given like this. So up to here, and then in between 0 to 1, so which is up, and after that, so this is okay. So this is our x and y. So this is the value 1. This is 1. So in here we can note this from here. So we can look at this point and this point. So these 2 points whereby f is not smooth. Okay. So if f is not smooth, so we can exclude these 2 points when we want to construct our density function here. So f is not smooth over here, then we can exclude 2 points when constructing small f. Okay, because here we want to use the differentiation, right? So that's why we don't have to use it. So this is our f, then we can exclude it. So by using it, so we differentiate this function, then so we can have so f is equals to, we differentiate it. So differentiating 0, so we'll get back to 0. So when x is less than 0. So next, when x is in between 0 and 1, so this is x, we have this is 1. When 1, we differentiate, we get 0. So if you're looking at the graph here, then this is doesn't really matter whether we put in the value or not the value. So the graph, it looks like this. So this is from 0 to 1. So from here, then you can see this is actually the uniform distributions. So you should have seen this before, okay? Okay, so so this is what I have discussed just now. F is not continuous at 0 or 1, x equals to 1. So the value f0 and f1 may be defined in any point, but it won't affect the result. So that's why we may exclude it. So if we take f0 equals to f1 to be 1, so we get our function to be like this. So what we can do, we can assume this. We can put it in any way, but make it easy, we can put it over here. So the reason is just like, in fact, you can put these two values to be any way. Okay, so we may define like this, for example, here, 0, and let's say you can put a point here and I put a point here. It doesn't really matter. So like what we have discussed just now, okay, like here, like I mentioned here. Okay, so if you look at so this x and y are not exactly the same, right? So it's different by 2 points here. However, when we compute the probability, they give the same probability, or they give the same distributions. So that's why it doesn't matter you take x or take y. So these two values, it will not affect the result. Okay, so that's why you can put these 2 points in anywhere. So to make it easy, in this example, so instead of putting here, then we can just define here. Okay, so that's why by using this, then we can define our fx becomes like that. So that is 1 whenever x is from 0 to 1, 0 when in other value. Okay, so next examples. Okay, we have this. Fx is given like this. Cos x whenever x is in between 0 to pi over 2 and 0 in other values. Okay. So let's look at the graph. So the graph is quite straightforward. Cos x in between 0 to pi, so which is given like this. Inclusive, right? So including here, and it will go down to here. Okay. So in other, you will get 0. So the graph will be like this. So this is xy exit. So again, as I said, so we have to verify, make sure our function fulfill these three properties. These two properties. First of all, f must be greater than equals to 0, and if you integrate over r, it gets value 1. Okay. So we verified it. Okay, I think first of all, I think it's clear. Fx is greater. Okay, so if you look at the graph here, for any x in between, for any x actually, for any x. And secondly, so if we integrate f from negative infinity to positive infinity, so here returns value 0. So that's why we only need to look at 0 to pi. So this is equals to 1. So when we have 1 and 2, then we can see this is a PDF. Again, just a PDF. So I think this one, we go back to these examples. So we can do it analogically. Okay, so we have a small f here. So we can use our formula to construct our capital F. So or the other way around, you may use a formula to derive our small f from this capital F. Okay. So I think I can leave it to you. Okay, so the last part for this, we have this. So this is a sigma field generated by a random variable. So this is another way for us to construct a sigma field. Okay. Yeah, let's look at the definition for it. X, okay, so X is a random variable from omega to R. Okay, so then the sigma field generated by X will be this. So that is all the pre-image for it. So if you want to take the language, so that will be like this. So given a random variable X from omega to R. So again, we always assume the sigma field omega is F, and we always take the standard scheme, the Borel sigma field for R. So in this case, so F is already a sigma field for it. Then what we can do is we can just define a sigma field generated by X. So this is all the inverse images of Borel set, yeah, of course, under X.
Excuse me. Yeah, can I just clarify something? So when you write the function x maps the sample space to the rails, and then below that you put f to the Borel set of rails, do you also mean that x maps f to Borel set of rails?
No.
Okay.
No. Actually, X is a function defined on the sample space, okay, not the sigma field. The reason is we always equate with this F, so we just put it over there. But X, how should I say? It should be like this. Yeah, okay, thanks for raising this. It's a bit confusing. I'm losing it. Okay, so usually when X, right? So we put it something inside here. So this thing must be an outcome. Right? So this is for random variables. X is a random variable, so those are inside here, whatever it add on will be outcome. So which is not different from P. So P, that means you have to add on inside here. So this is an event. So this is a probability measure. Right, so the reason is because of in probability, we are not just look at a set theory. So that's why when we have a sample space, we always need to look at the event, that is the sigma field, as well as the probability. So that's why we always put all these things together. But just to highlight, just to remind you, okay, good questions. So X is defined on omega, okay? Or you look at here, so it acts on outcome, sorry. Okay.
So why does the second one change? Are you trying to say that the sigma field is the Borel set of R's, or is it changing?
Not changing. I'm just saying that when we have a sample space omega here, it's always come up with one sigma field. Okay.
Okay.
For this R, we always equate with BR.
Oh, right? Okay, I understand now. Right.
Okay. So thanks. We just like supposing, let's say all of us are already married. So when we come to some kind of gatherings, we always bring our couple. Okay, so I bring my wife, you bring your wife. Okay. But the invitation only for me, not for my wife. Okay, but I will bring my wife along with me. So something like that. Okay. So yeah, good. Sorry, I think but we always do it this way. remember, x is a function defined on omega. So that means those inside the bracket must be an outcome, cannot be a set. When we talk about probability, inside here must be an event, but not outcome. Okay. So this is things that I think need to clarify. Okay, so what we can do, we can just take this sigma x to be all the inverse images of Borel set under this x. Okay, again, first of all, we need to verify that it satisfies the property, the definitions. Okay. But I'm not going to do it over here, so but leave it to you. All right. So it had to satisfy these three things over here. Okay, so then I leave it to you. Okay, so again, a note. So you need to verify sigma x fulfill the action 1 to 3 in definitions 1.1.1. Am I right? So actually, it's not hard. So first of all, you can see omega is equals to x inverse of r, right? So maybe I'll put it this way. First of all, okay, R is a Borel set, okay, and omega is equals to x inverse of R. So using these two, so then omega must be inside here. Okay, so this is and secondly, so let's say if you have something inside here, so let's say x inverse. Okay, maybe I just put one more. Yeah, the third one. So let's say if A is inside here by the constructions, so it must be in this form. So then A must be equals to x inverse B for some Borel set B. Okay, this is the one. So then you can see the complement of A must be equals to the complement of the pre-image of one Borel. So then this is the one, and also because of this is also an event. So by using these two, this and this, then we can see that, and the definition as well. So then we can see AC must be belongs to sigma x. And the third one, then you go and do it on yourself. Okay. So you have to practice to do this kind of explanations over here. Okay. Okay. Why we want to have this kind of definitions here? Okay. Okay. So just give you remarks here. First of all,